Okay, so we are in, what are we in here? Generalized linear models with examples in R, chapter 3, and we're on question 3.4. Um, so, uh, in the chapter, we're given this formula for what is called Cook's distance, and we'll talk about that in a second. Um, and then we're told here that we can rewrite an expression for Cook's distance like this, right here. Also in the book, all of the little i's here have been omitted, but I think that the R should have an I, and the H should have an I, and the D should have an I. So, but I just replicated it directly from the book. Okay, anyway, so we're told that we can use another expression for Cook's distance, which is this right here, and we're supposed to interpret this in this form here. Okay, so you can read my my answer here, but I'll just try to talk through it here. Okay, so let's first get familiar with the terms. So we have mu hat and then mu hat subscript I. Okay, so mu hat is the vector of the fitted values when we run a regression on all data. Okay, so in other words, we have our data, and we have our outcome y, and then our input or our predictor variable x, or maybe several predictor variables, x1 through xn, say, or xp, I should say. Okay, and so after that, we will get a we'll get a regression formula out of it. We will have fitted the model, and we'll get values for like the beta coefficients, etc. And then if we plug back in the predictor variables into that equation, we will get expected values for the output. Now, of course, the expected values and the actual values are going to vary a little bit, and that's because of the randomness, the random component in the regression. Okay. Now, mu hat sub I is the same thing, except for we have omitted observation I, whatever I is, okay, and we're going to do that for each observation, okay. So DI refers to just one instantiation of this equation over here for one observation, okay. So now we know what mu hat is and mu hat sub I is, and now notice that we have that same expression over here, and so we have that term transpose, these are vectors, so we transpose it and times the same term. Okay. Well, we can just think about that as squaring it, right? So we could just think about that as just squaring this value. That's what this expression does. So what do we have then? Well, what we have is the squared distance between the fitted values on a regression where all of the data is used minus the fitted values when all but observation I are used. Okay, right? And so what's going on is if a particular observation is very influential in the fit of the regression model, then when I remove it, then this distance, or in other words, the squared distance, the whole numerator here, will get bigger. Conversely, if that particular observation is not very important, right, it doesn't really change. So if we run a regression and without that observation, it doesn't really change the fitted values, then this numerator will be small. Okay, so this numerator really is capturing the influence of any particular observation on the fit of the model. Okay, so then what about the denominator here? So we have p prime, which is the total number of parameters, so all of the beta coefficients plus the intercept, all of the slopes plus an intercept, or all of the intercepts, or whatever, multiplied by the estimated variance. Okay, so what's going on here? So I've said that we've already found the influence of observation I with this up here, okay? But we probably want to normalize this to something, okay? And so I want to convince you that this term down here is a good thing to try to normalize by, okay? So let's just look at the variance, the estimated variance, as squared, okay? Well, think about what happens as there's more variance. As there's more variance, DI will get smaller, right? Which, in other words, the estimated Cook's distance, or the estimated influence of observation I, should diminish as the variance gets bigger. Now, I hope that makes intuitive sense, because the more variability there is in the data, it means that the data has more influencing factors than what we are accounting for in the regression, right? That random noise is actually, there are causes for that random noise. We're just not accounting for them, right? So the greater the variance, it means that there's more influence that is not being captured by the regression model. And so if there's more influence in these factors, well, that necessarily reduces the amount of influence given by any of the observations, okay? Now, what about the p prime part? Well, as p prime, as the number of parameters increases, in any given regression, the variance, the estimated variance, should decrease as we increase the parameters, right? So think about a situation where we have a lot of parameters and still have very high variance. Well, now, the amount by which high variance is diminishing the estimated influence of any particular observation should be magnified, because we had more chances to reduce, or we had, well, it's a weird way to say it, but I'll just continue. We had more chances to try to reduce the variance to to an important degree. And so if we have high variance and high parameters, then we should then we should say, wow, there's a lot of unaccounted for factors that are affecting the fit of this particular regression, and therefore we should proportionally diminish the amount of influence we are ascribing to any particular observation. I hope that makes sense. Okay, we'll call that good.